Good morning. Now, this is class 6 of digital electronics. Now, as a continuation of our last class, in the last class, we have studied about theorems. I think we have studied up to theorem 6. Now, we are going to study about theorem 7, its proof. Okay, now, theorem 7 is a plus 1 is equal to 1. So, here you are demonstrating it with the help of an OR gate. Why? You are dealing with addition operation. So for addition we use OR gate, and for multiplication we use AND gate. That all we have studied in the last class. So here as one of the inputs of OR gate you are giving 0 and the other one as 1. So in place of A we are giving 0. Okay, this is actually A. So here 0 plus 1, A is 0, so 0 plus 1 is 1, so it is proved. Then you are giving the value of A as 1 and the other output will be kept as such 1. So what will be it? A plus 1 will be A is 1, so 1 plus 1 it is again 1. So this law A plus 1 is equal to 1 is satisfied. Now theorem 8, you are dealing with multiplication operation, that is dot, so you will opt for AND gate. Okay, so here you are first of all you are putting A equal to 0 as one of the input and the other input is given as 0. So A dot 0 will be A is 0, so 0 dot 0 it is again 0. Then we are giving A as 1, 0 is kept as such, so A dot 0 will be 1 dot 0, it will be 0, so A dot 0 is 0. So that theorem is also proved. Then theorem 9, that is A bar the whole bar is equal to A. You know that is complement we have studied. 1 complement is 0, 0 complement is 1. Now if you are using one more complement, what will we do? That is, if we are giving like this, what will happen? This is also will become complement, that is equal to 1. If this is again given one complement, this will be given complement, so one complement will be 0. That is what we are going to prove now. Here NOT operation, that is complement, so NOT operation for use NOT gate. A is 0, when it goes through the NOT gate A will become A bar. So since A is 0, A bar will be 1. Again we are giving that A bar to another NOT gate. So what will happen to A bar? A bar the whole bar, that is 1 bar. 1 bar is 0. Okay, see, that is again the input, we got it as A. Now again A is given as 1, so when it goes through the NOT gate, what will become? A bar, that is 1 bar, that is 0. And again this is going through a NOT gate, so what will happen? A bar is again will get barred, and then 0 will be again we will giving a bar, so that will be 1. Okay, so A bar the whole bar equal to A. Now duality principles means that Boolean expression it will remain valid if operators OR and AND are interchanged. That is, if you are having a Boolean expression, that is if you interchange OR and and 1 is replaced with 0, then the expression will not get changed, it will remain as such. See, there are 3 examples. A plus 0 is equal to A. Here we are going to replace this OR operation, that is dot plus with the dot, and 1 is 0 is changed to 1. What is that? A plus 0 is A dot 1 equal to A. These two identities already exist. Now again A plus, example 2, A plus A bar equal to 1. That is, now we are going to replace this and addition operation with the dot. A bar is kept as such, 1 is replaced with the 0. Is there any identity like this? Yes, of course. A plus A bar is 1 and A dot A bar is 0. So Boolean expression remains the same. Next is A plus 1 equal to 1 and A dot 0 equal to 0. A plus 1 equal to 1, A dot 0 equal to 0. That is, plus is replaced with the dot, 1 is replaced with 0. Here also 1 is replaced with 0. So these two identities also already exist. So even if we change and or and operation and or operation is interchanged, or 1 and 0s are interchanged, then the Boolean expression will remain as such. There will be no change. Next is multivariable theorems. This theorem refers to the condition when more than one input to the logic gate variables. Okay, the theorems are given as such. Here there are 18 theorems. So theorem 10 and 11. What is it? You might have studied in your lower classes. A plus B equal to B plus A. What is that? Commutative law of addition. A dot B equal to B dot A. What is it? Commutative law of multiplication. Okay, next is a plus, first b plus is given in brackets equal to a plus b plus c, that is associative law of addition. Then a dot b dot c equal to a dot b dot c, that is associative law of multiplication. Next, a dot b plus c equal to a dot b plus a dot c. Then a plus b dot c plus d is equal to a plus c plus b, a dot c plus b dot c plus a dot d plus b dot d, distributive law. So this one you please check in your textbook. I think there is some mistake, so this is the correct expression. Okay, if there is anything change in your text, please correct it as follows. Then a dot a plus a dot b is equal to a, that we will prove later. Then two most important theorems. This is a very important theorem in Boolean expression, that is De Morgan's theorem. One statement is a plus b the whole bar equal to a bar dot b bar, and the second statement is a dot b the whole bar equal to a bar plus b bar. This we will prove later. This is a very important session of this topic. Okay. Next, theorems 10 and 11. Here we are going to prove this, that is the commutative law of addition and multiplication. Okay, states that the order in which the variables are odd and makes no difference. Let's prove. That is, so first we are going to prove this a plus b equal to b plus a. So we are dealing with addition operation, so we use OR gate. We are giving two inputs a and b. So what will be the output of OR gate? It will be addition. So what will be a plus b? Okay. Then now you are changing the order of input. In place of a you are giving b, in place of b you are giving a. So what will be the output? B plus a. So a plus b is b plus a. Now we are verifying it by putting zeros and ones for the values of a and b. Okay, so we are putting a and b as 0 first of all. 0 plus 0 is 0 plus 0, again that will be 0. Now a is taken as 1 and b is given zeros. Then b is given 0 and 1. So what will be 1 plus 0? 0 plus 1, it is 1. Similarly this. Now this proves actually the commutative law of addition. Now we are going to learn similarly the commutative law of multiplication. Since multiplication we use AND gate. See, a and b is given to an AND gate. So what will be the output of AND gate? A dot b. Now we are going to change the order of inputs. B is given first, a is later. So when you goes through this AND gate, we got b dot a. Then similar to this, you are substituting the values for and proving this theorem. Okay. Next, theorems 12 and 13, that is associative law of addition and multiplication we are going. That is here there is a grouping comes. Okay, this one. A plus b plus c, then a plus b plus c. So b plus c is grouped first, that we are going to prove. Then the second one. Okay, so first what we do is that we are using two OR gates. Why are you using two OR gates? There are two additions, so you need two OR gates. Now let us see the input. So first of all, b and c is added first. It is then added with a. Okay, this is how you interpret this statement. That is, b and c are given separately as the inputs of an OR gate. They are AND. That means they are added, and that AND or the added product is again added with a. Okay, so first you give an OR gate. You are going to add b and c. So b plus c. Then b plus c, that is the output of this OR gate, is given as the input of the another gate. So b plus c will be the in one of the inputs of this gate, this b plus c. Okay, this will be a. So what will be the output? A plus b plus c. Okay, so that is how we proved this, the statement a plus b plus c. Okay, now this is not complete. Again, that is equal to a plus b plus c. So here this you understood. B plus c is added first. It is given as the input of another gate, and it is again added with a. So from this, how can you write this? That is, a and b has to be added first, and then that added one will have to be added again with the c. See, a and b is added first, a plus b. It is given as one of the input to the other OR gate. C is the other one, so output will be a plus b plus c. So that theorem is also proved. On combining, we can write this one. Okay, associative law of addition. Similar is the case for multiplication also, but instead of OR gate we use AND gate. See, A dot B dot C equal to A dot B dot C. So first this one, B and C has to be multiplied. Again that has to be multiplied with A. So first B and C, and again output is B dot C. This is one of the input of the other AND gate plus A, then also another one A. So A dot B dot C. Now about this one, A and B is first of all AND, that is A dot B. It is one of the input of this AND gate. The other input of AND gate is this one C. So the final output will be A dot B dot C. Okay. Now the last one, theorem 14 and 15, is the distributive law. So distributive law, here it comes, this one, A plus B dot C plus D is equal to A plus C, this one. So this we are going to prove it step by step. So taking the left hand side first, this one. So you are dividing it into two cases, four cases, and we are giving different values for A, B and C. First you have to prove this part, that is A dot B plus C is equal to A dot B plus A dot C. Okay, that is a distributive law, right? A dot B plus C equal to A dot B plus A dot C. So first we are going to prove. We are giving the values of A, B and C as 0. Now substitute the values for each. 0 plus 0, 0. Then again 0 dot 0, 0. Here 0 dot 0, 0. 0 dot 0, 0. So 0 plus 0, 0. And similarly you are using different values. A is taken as 1, B and C is kept as S. Then A is changed to 0, B 1, C 0. Then case 4, 5. So these 3, 4, 5, within these 5 cases, that is we are just changing the values for A, B and C, and accordingly we are substituting the values and proving the theorem. So you have to study all these 5 cases. That is how the values are interchanged. And from all this we can verify this theorem. So first you are using a OR gate. B and C is added first, so you get the output as B plus C. It is one of the inputs to this AND gate. Another input is A. So what will be the output? A dot B plus C, because you are using AND gate. Then A and B is added first and multiplied first, so A dot B. Again another AND gate, A and so A dot C. Now A dot B and A dot C is passed through an OR gate, so that will be added, that is A dot B plus A dot C. Okay. Next, the last theorem, A plus A dot B equal to A. Here in place of A, you are just multiplying this A with a 1, that is A dot 1, that is A itself, A plus B. Okay, this one like this. Now A is taken outside, so A dot 1 plus B. But 1 plus B or 1 plus A is what? 1. That today we have proved. So that will be 1 plus B is 1 or 1 plus A is 1. So A dot 1. What is A dot 1? A. This is how you prove a Boolean expression. Okay, so today this is enough. Please go through these theorems and try to understand it. Okay.